My favorite. Would you like to play yours aloud or mine aloud? These are yours headphones. Are you sure?
Good afternoon. Welcome to Oceanography. Today we'll be continuing our lecture on ocean water. It's the way in which water properties promote structure, or what we call structure within the water column, and some aspects of ocean chemistry. We may not cover all of the material I'd like to touch on, all the material from chapters 6 and 7, which contain a lot of material, some of it quite challenging. We'll get to as much of it as we can and then carry on next week if there are other concerns or things we don't quite get to, or people have particular questions. I want to also touch today on milestone 1, and then also a little bit about the team homework this week, which is might be a little challenging because it involves these contouring exercises. I did go over contouring last week, but I want to make sure everybody's on the same page with this so that you'll all be able to complete the questions. And hopefully the material that I'll cover today will give you the pointers you need for answering some of the other questions in the team homework. So before I get started, are there any questions? I love to have questions because it lets me know that people are out there and they're listening and they're interested in what's going on. So anybody, any questions, anything about the milestone or the homework or any of that?
Are we going to be following up on milestone 1? With
yes, we are, in fact. Yeah, what we're going to do is we will have, so you've all turned in, everybody turned in, and I've looked at, and Carrie has looked at the assignment. But as I said, when we introduced the concept of the team research project for the semester, is that you guys were making a proposal. Each team was making a proposal for the subjects that they wish to consider, the topics that they wish to consider in their research project. And what we want to do as a follow-on to what you've submitted is go back and have a conference. So Carrie or I will meet with each of the teams individually. We'll spend, probably 20 or 30 minutes going over your submission. And depending on what the different teams have turned in, and we're going to offer suggestions about about focusing the project ideas, or where you can find resources or other considerations to make sure that each team takes on a project that's going to maximize their possibility for a good grade and for learning. Okay? So these conferences, they'll be set up as Zoom conferences, and the way this works is you'll sign up for different slots. Carrie will be posting different sign-up sheets, and so all the teams will pick a time when they're available, and Carrie and I will meet with you individually during those time slots. Okay. Other questions? All right, well, let's get started then. So you'll recall in our lecture last week, Tuesday rather, we've been talking about water, and we started talking about what an amazing compound water is, that it's unique among compounds that we know of, certainly in the Earth environment. It's the only compound that occurs naturally in all three states of matter, liquid, solid, gas. And that in these different states, it displays properties which are very unusual for gases or liquids or solids, relatively speaking. And a lot of these properties, somebody has got there. Isabel, thank you for muting. A lot of the properties are okay. Isabella, can you please mute your microphone? I'll mute you. There you go. A lot of the unique properties of water, or the special properties of the compound water, are caused by the hydrogen bonding and by the way in which the hydrogen and oxygen atoms organize themselves within the water molecule. So the hydrogen atoms sort of tend to be at one side of the oxygen atom, with an angle of approximately 105 degrees between the two. And so this produces a negative side in the water molecule and a positive side. So it's a dipole. There's a polarity in this molecule. And this polarity allows water molecules to bond together in the liquid state. So the bonds form. These are chains of molecules that are bonded together. Of course, this is happening at a molecular scale. So thinking about things like chains and solids is analogous to what's happening physically, but we can think about it that way. And so on average, there are I think 3.5 molecules bonded together, so that each water molecule is connected to 3.5 molecules, and the average angle between the molecules is 105 degrees. As we lower the temperature, there's less energy, and eventually when everything binds together in a rigid lattice, when all of the water molecules are bonded to all of the other molecules, the average angle between molecules increases to 109 degrees. And this increase in the angle means that the spacing, the density of the water actually decreases. And so this means that solid water, ice, has is less dense than liquid water at its maximum density, 4 degrees Celsius. So ice floats. And so this is one of the unique properties. Other unique properties are so each molecule is bonded to 3.4 liquid molecules, angle of 105 degrees. And then when it's solid, it increases to 109 degrees. So you can see the change in density here represented in this cartoon. And the ice floats, which is an important thing if you think about that. If lakes froze over, and then when the water froze on the surface, it sunk to the bottom. Solid, frozen lakes would be solid ice from top to bottom. It would make life difficult for fish and other organisms. Well, that doesn't happen. Ice floats, and that is one of the many properties of water that make it so special and allow life to exist. Another extremely important property of water for our purposes, as we're discussing the way in which heat is distributed, or heat that arrives from the sun is distributed around the planet. Water displays a property called latent heat. And so what this means is that it takes energy to change water from one phase to another, to change ice to liquid or liquid to gas. And this energy has to do with, or this energy is utilized in order to break or form hydrogen bonds, depending on if you're going from a dense, from solid to a liquid, or a liquid to a solid. Going from a solid to a liquid, you have to break hydrogen bonds. Going from a liquid to a gas, you have to break even more hydrogen bonds. In fact, to go to a gas, you have to break all of the bonds. And so that breaking of bonds, or formation of bonds, depending on which way you're going, requires energy to be either put into the system or removed from the system. And this energy is called latent heat. And so there's latent heat of evaporation, and there's latent heat of fusion, depending on which direction you're going. Now, the fact of this heat latency means that there is this latent energy, or latent heat energy, that's bound up or represented by water in whatever phase that it's moving. And so particularly important is the way in which the latent heat of evaporation, or vaporization, it carries with the vaporized water. And so you have to, in order to evaporate water, you have to put in 540 calories per gram of water. And when that water then condenses and falls as rain, that heat is released. And so by forming water vapor at one part of the planet and moving it to another part of the planet, you can move not just the physical water, but the heat, this heat energy that was contained in the vaporization. Well, this process has the result that it can control climate and can determine, very, very different climates across the United States and across other bodies. So the example that we gave is, comparing the southwest of the United States, specifically southwest California, and the desert states, and we notice that these tend to be hot and dry. Why are they hot and dry? Well, it has to do with the water that's evaporated. So cooling water takes a great deal more energy to evaporate. So there's less water carried. Warm water in the Gulf of Mexico, for example, water evaporating off the Gulf of Mexico does so at a higher temperature because the water is warmer. So more water can move in and to the southern states. And so the difference in the water body from which the precipitation is forming makes a huge difference in terms of the average temperature in those areas. And then we also pointed out, for example, the difference between San Francisco and Norfolk, Virginia, and noted that the two areas have similar average temperatures, but display a greater range. Questions? Okay. So that was sort of reviews where we were. We also looked at the dissolving properties of water. When water is called universal solvent, And so most organic or ionic compounds can dissolve in water. And the example we gave is salt, sodium chloride. Sodium chloride as a solid form is present as a crystal, and the sodium and the chloride molecules are bonded together. When salt dissolves in water, these the same abundance of sodium and chloride atoms are present in the same proportions, but they're no longer bonded together. And so this is a dissolution, a solvent, a solution of salt in water. So the properties of solutions are that you can add the solute to the water, as you add it, the mass of the water, the mass of the solution increases, but its volume stays the same. So that salty water is denser than fresh water due to the addition of sodium chloride and other compounds. What are the other compounds? In the case of ocean water, there are a whole range of compounds. So sodium chloride, the is the most abundant, followed by sodium, followed by sulfate, followed by magnesium, followed by bicarbonate and calcium. So it's actually in terms of abundance, it goes chloride, sodium, sulfate, magnesium, calcium, potassium. Bicarbonate is important, as we'll discuss, for other reasons. And so these compounds are all present. And the other factor here includes most of the known elements on Earth, which are dissolved, many of them in very, very small quantities. So it is true that you could, if you had enough water and enough energy, ocean water, you could derive gold. There is actually gold and other elements dissolved in water, but they're present in minute amounts. Okay, and then the other important concept that we introduced here was the concept of constant proportions. And so wherever you go in the oceans, you could take a sample of that ocean water and measure different concentrations of the dissolved solids. So, you could go from a 30%, 30 part per thousand salinity to a 35 part per thousand salinity. And you would change the amount of water present, but the proportion of the dissolved solids would stay constant. So this is the principle of constant proportions. Okay. Now, the other concept that I introduced was this concept of residence time, and I struggled a bit to explain this without a blackboard behind me, and so I've prepared a slide here to help to explain this. And so the concept of residence time is really a useful way to think about fluids in particular moving in and out of reservoirs. And it's useful because the arithmetic, although you can make it a lot more complicated with calculus to determine rates and so forth, but the basic arithmetic is very straightforward and gives you sort of easy answers to questions. So let's consider the way you think about this is you have a volume, a reservoir, here represented by M. So this is a volume. And the F in or the F out are the flow of material into or out of the volume, the reservoir. So M is the reservoir, F in or F out are the rate of flow into or out of the reservoir. So, what does that mean? So if you had a lake, for example, or let's just take the example of a lake, and let's assume that it was that it had a total volume of 1 million cubic meters. It's actually a fairly small lake, and there's a stream flowing into the lake at a rate of, say, 10 cubic meters per minute. If the volume of the lake doesn't change over time, we would have to assume that there's also an output from the lake an outgoing river or absorption into groundwater, evaporation, whatever, and that this out, F out, has to be equal to the F in. Flow in has to equal the flow out if M does not change in size over time. Well, knowing these facts, we can calculate the residence time, tau, as a factor of minutes. So if we assume that the flow is steady and conservative, so it's not changing within the volume, then residence time is given by this simple equation of volume divided by rate. So an example of this, if we assume that try to write on this page here, if our lake volume equals 1 million cubic meters, and our flow in equals, say, 10 cubic meters per minute, right? And the volume of the lake does not change. We know that F in has to equal F out. Well, then it's very simple. So we take 1 million divided by 10 equals 100,000 minutes. So that tells us that any parcel of water has an average residence time in the lake of 100,000 minutes. And okay, so that's considering all of the water that's present in or out of the lake. If we were to imagine that this was a volume of seawater, so not pure water, but seawater, we could apply the same thinking to whatever dissolved components were present in the water. All right. Well, that's where the concept of conservation comes in, because compounds are not always conservative sometimes, or they have different degrees of being conservative. By conservative, I mean tending to remain the same over time. So this is a chart of different elements found, different dissolved solids found in seawater. And all of these compounds are reacting to different degrees with the total environment of the ocean. So for example, calcium here is present, and it's present in large amounts, significant amounts, but it's interacting. So calcium is forming, being removed from seawater by organisms to form their shells, and those shells sink to the bottom and are preserved. So there's an output of calcium, and there's an input, so more calcium comes in from runoff. You recall that the calcium is a component of runoff, of the water running off from the continents and entering into the oceans. So this is a not perfectly conservative compound, and so we can measure conservation in terms of the expected residence time for any unit of any element in water. And if we do that, we find that chloride has the longest residence time, whereas sodium is less, and so forth. And then, these are the concentrations of these different compounds in seawater. So if we were using chloride as a tracer, or salt as a tracer, on how long compounds remain, how long water remained in the ocean or in ocean processes, chloride would be a good compound for that comparison. Is that clear? So this concept of conservation is one of the, and using chemical tracers on conservation is one of the ways that we can think about understanding changes to the ocean over time, and also very importantly, how things are interacting. So I picked the example of calcium because that's pretty clear that, calcium is being removed to form shells, and then some of these shells are permanently or over longer periods of time removed from the ocean because they sink to the bottom and are not dissolve. Of course, some calcium is redissolving, as we talked about with the calcium compensation depth. So calcium that sinks into the deep ocean does tend to dissolve, and so re-enters the ocean. Other compounds, manganese, for example, and where manganese on this is, and down here, tends to be removed or added as ocean water filters through the mid-ocean ridges. And so one of the problems that chemical oceanographers had before we really understood the dynamics of mid-ocean ridges and the way in which new ocean crust is forming is trying to balance the residence time of these compounds against what was observed. And it wasn't until oceanographers and scientists began to understand that there was this constant circulation of ocean water through the, down into the earth and interacting with the magma and then re-emerging with different properties and carrying with it different compounds, that we understood or could begin to understand, how these different residence times were maintained over, geologic timescales. Okay, I hope that explains a little bit better this concept of residence time and conservation. And we'll come back to that with more sort of simple calculations as we go forward with the course. But these are important concepts to have under our belts. Okay, so we've been talking about salinity and measuring salinity, determining what the salinity of ocean water is very important for understanding how ocean water is structured. Because remember, salinity is one of the things that causes ocean water to have different densities. Okay? So if we wanted to measure salinity, what we're trying to do is to measure the concentration of dissolved solids, salt, in the ocean. And salinity is calculated in terms of chlorinity. So salt is 1.8 times the chlorinity is the salinity of the ocean. This adjuster here is to allow for the other components of seawater. So a physical method for measuring salinity would be refractometry. Refractometry. What do I mean by refractometry? Well, refraction occurs when you have an energy, a medium, such as light, passing through a medium, and if the light passes through a media of two different densities, then there's a change in the speed with which the light or sound can pass through that medium, and that speed causes a refraction. Of course, we're all familiar with sticking a straw into a glass of water and observing that at the surface of the water, the straw appears to bend. Why is the straw appearing to bend when it sticks into the water? Is because light travels through air and water at different rates. And so at the interface, you see the shift in that rate. Well, the same thing can be applied to light passing through water of different densities, and different densities are caused in part by the salinity. So a salinometer works by looking at finding this refraction gradient and putting it on a scale. And so this is a very accurate, simple way to measure salinity. Probably many of you have already done this. You take the salinometer, you put a drop of the liquid that you're trying to test, the water that you're trying to test, onto the screen. You lower the screen so it's flattened out. And then by looking at a light source, you can see where this refraction occurs. And the more refraction indicates a higher density, a higher salinity. Less refraction indicates a lower salinity. And so this is an accurate measurement of salinity. In the olden days, and I'm old enough so when I took oceanography as an undergraduate, as a lab course, they had us titrating salinity. So they used to figure out in the olden days, they would take samples of seawater and they would have to either titrate them at sea or bring the sample back to land, carefully containing it so it wouldn't evaporate, and then titrate it. So it's titrated in silver nitrate. And the process is you're mixing the silver nitrate. It's sort of a pink material, and you add reactants until the color disappears. And it's laborious. It's accurate. You can determine to within about 0.01% of the chlorinity, 0.01 per mil of the chlorinity. Well, nowadays, unless there's some special reason for doing so, salinity is determined in terms of the conductivity. So the tendency of water to conduct electricity. So fresh water really doesn't conduct electricity very well, but as you add salt to the water, it becomes more conductive. And so by measuring the conductivity and by applying various corrections to that, the tendency of water and tendency of an electrical current to be conducted across a cell of the water provides another very accurate, and even actually more accurate than the titration method. So these are some pictures of what are called CTDs. And if you had to find one instrument that sort of is emblematic of oceanography, it would be the CTD. What does CTD stand for? It stands for conductivity, temperature, and density. Depth, excuse me. Conductivity, temperature, and depth. So what a CTD does is it has a cell in here. So there's a pump that pumps seawater through a cell at a constant rate. And there's a current induced across this cell, and the drop in current is measured at the other side. And so this current drop then gives a very precise estimation of the conductivity. And by adjusting for temperature, and you actually have to adjust for latitude, the salinity can be determined very precisely. So conductivity. There's also a temperature sensor in here. So there's a thermometer, digital thermometer, that's also measuring the temperature of this same passage of water. So you get simultaneously a measurement of the salinity, because the conductivity is translated into salinity, and then the temperature. And finally, there's a pressure sensor. And the pressure sensor, of course, is the pressure that the instrument is experiencing is proportional to the depth of the instrument in the water. So as you lower it deeper and deeper, there's more water weighing down on the top of the instrument as it descends deeper and deeper into the water. And that pressure increases, increases roughly by roughly, well, it's 1 bar per 10 meters. And so we can measure precisely the depth by measuring that temperature. You have to also adjust for other factors, but the depth is measured precisely. So that means that if we lower one of these instruments down into the water, we can know what its temperature and salinity is at every depth, okay? And this is describing some ways in which the devices are used. So here's the CTD, and then the CTD is embedded here in this picture. So here's the CTD at the bottom of the instrument. This thing is called a rosette. And this is, I don't know if anybody's been to sea here, but oceanographers spend a lot of time taking this big thing, getting it over the side, lowering it down as far down as they can go in the water, bringing it back up and getting it back on deck. That sounds easy, but keep in mind this thing weighs several hundred pounds. It's at the end of a cable, so it can be quite exciting if the weather is rough, getting this thing safely overboard, and then even more challenging can be getting it safely on board again and roping it down. And so myself and my students have had some exciting moments over the years deploying and recovering CTDs. All right, so that's the, and I guess one other thing I'll point out, this is an altimeter, and a short range altimeter. So this is pinging out, and what you use the altimeter for is to lower the instrument close to, but not all the way down to the bottom of the ocean. So when you get within about 10 or 20 meters of the bottom, you start getting a feedback from this the short range altimeter, and you lower it down. So typically, if you're watching a CTD go over the side, you watch it go down and down and down, and then it starts picking up the bottom, and you tell the winch operator, okay, slow down, we're close. And then they keep lowering it down, and when they get to 5 meters, 3 meters, 2 meters, you say stop. And they stop and then start winching it back up. Okay, so the altimeter keeps you from running this expensive instrument into the bottom of the ocean when you're trying to make a measurement. The other thing we've got here is something called a Niskin bottle. And so then what the Niskin bottle does is it returns a sample of water back to the surface. So what you see here, in this case, the Niskin bottle is deployed in its open arrangement. You see here that this is a tube, and it's open at the top and the bottom. So as the Niskin bottle is lowered through the water, water flows freely through it. Okay, if we wanted to get a sample of the water at any particular location, we'd want to somehow or another cork up that bottle, cork up that tube, so that the water that was flowed through it in a particular location in the water was trapped and could be returned to the surface for sampling, for measurement. Okay, so how do you do that? Well, if you look closely here, you can see that there's a surgical tubing attached to the top of the float, and there's a similar one on the bottom. So let's see if I can draw a little sketch of how this looks. So we've got the tube like this. Top and bottom. And the top plug is like this. The bottom plug is like this. And then connecting these two is powerful surgical tubing. And then there's a trigger here that you can't see very well that attaches this end of the plug to that end of the plug. And so this is stopping. Okay. To take the sample, we pull this trigger back, and that allows the cord to pull these two stoppers closed, so that when if you trigger this, break this connection, allow the spring to pull these two stoppers together, the tube comes back like this. So there's the stopper on the top, the stopper on the bottom. There's a gasket around the top and a gasket around the bottom, an O-ring actually. And then the spring, the surgical tube, in the middle holds the two ends tightly together. And then typically there's a little spigot on the side, which didn't do that. That allows you to decant a little sample. And so that's what you're seeing in this picture here. So each one of these Niskin bottles, and you can see that they're different sizes for different amounts. So these are probably 10-liter bottles. These are probably 5-liter bottles. And maybe on the other side, there's a 2-liter bottle. And so this is what they look like when they go over the side. And this sample has been brought back on board, and all the stoppers are closed. Everything has been fired. And then there's this little spigot here. And then once you get it back on deck and everything is roped down and you're ready to go, then the scientists go out and they attach little tubes to these things, open them up, and then they can take multiple samples of the water that can be analyzed chemically for different properties. Okay, and this these Niskin bottles typically go down in multiples, 10, sometimes 15, sometimes 16 individual bottles, and they're arranged in a circle around this framework that lowers the whole thing to the bottom. Well, this is all connected via a conducting cable to the surface. So you get a real-time readout as the CTD, this is actually called a rosette sampler, because there's a rosette circular pattern of Niskin bottles, and then there's the CTD and the connection. So typically as you're watching, let's see what's coming up here. Yeah, so as you're watching on the surface, you'd see something like this. Okay, so here's a CTD profile. So as this device was being lowered down in the water, so here's pressure on one side and concentration of 3 different things that we're measuring. We're measuring, I guess actually we're measuring salinity, temperature, conductivity, and depth. So here's S is salinity, T is temperature, and O2 is oxygen. So these are 3. So there's an oxygen sensor also on this particular CTD. And so this is the pressure, and so this is roughly equal to 200 meters of depth. And so we go down through the water, and you can see that the salinity is relatively constant for the first one of these scales here. I guess this is for about the first 30 or 40 meters. And actually, this is more like, yeah. And so if you were watching this rosette go down, you'd be watching on the surface, and you'd see these lines tracing and recording the different properties of the water as the rosette got deeper and deeper into the water column. Okay? And so this is giving us some pretty essential information about the properties of the water as we go from the surface to greater depths. Now, I'm going to introduce a term which I've already sort of thrown around, which is the idea of the water column. And many of you heard this already, but the water column is refers to a continuous shaft of water going from the surface to the bottom. And so the water column, a water column could be like a 10-meter square shaft going from the surface all the way to the bottom. And within that, you would expect the properties of the water to change as you moved up or down in the column, in the water column. So if we look at these different properties that we've measured here, we can see that the salinity goes from about, what is this? I think this is temperature on the surface. I'm not seeing where salinity is written out. So the temperature is, looks like it's about 16 degrees in the water, it's 16 degrees Celsius. And that temperature is constant down to this depth here. And the salinity is constant down to this depth here. Okay, that's why, how do I know it's constant? Because this is a straight line. So it doesn't change with depth. Okay, and then we get to this point here, and all of a sudden the temperature starts decreasing and the salinity starts increasing. And I'm going to say that the salinity goes from something like 20 to about 35, and whereas the temperature goes from 16 down to about 10 or I'd say about 12 or 14 degrees Celsius. Okay. So, and then likewise, here's oxygen. So oxygen is also constant down to this depth here. And it doesn't start changing immediately, but as soon as you get under, there's a peak. So the oxygen actually increases, and then it decreases slightly. And so that the concentration of oxygen is less at 200 meters than it is at the surface. So what's going on here? What's happening? Well, of course, what we have to keep in mind is that the water column is stratified according to density. And the principal things that are determining density are the amount of dissolved solids, salinity, and the temperature. Of course, right? We talked about that. So as you increase the salinity, the temperature increases, the density increases. As you decrease the temperature, the density increases. So the denser fluids, of course, the denser seawater is going to sink to the bottom, and the less dense water is going to be displaced upwards. So you would expect to have less density at the surface and greater density as you went further down. Okay? So the fact that we're seeing this S doesn't change over something like 50 meters of depth, and T doesn't change over 50 meters of depth, what does that signify? Anybody have any ideas as to why, you know, under what circumstances you would have constant temperature and salinity over 50 meters of depth? Anybody got any ideas? I can call on somebody.
Is that like the surface zone?
This is the surface zone. Okay, but what about the surface zone? Yeah, you got the right term, Carly Ann, but why would it be constant? Why would the temperature not change? And what would determine the temperature?
And like how close it is to the sun, like the sun rays are able to penetrate that far into the water.
Okay, but it's got to be more than that, right? Because, you know, the sun rays are going to penetrate, you know, to different degrees the further deeper you go, right? So you would expect the heating to be greatest at the surface and become less as you went deeper, right? And then what about salinity? What would be determining the salinity? Any more ideas?
You would have actions of surface wind and waves and surface current that would continually mix the water.
Mixing, thank you, Damon. Yes, so the surface water is being mixed. And how do we know it's being mixed? Because it's not stratified. You know, this water is constantly being turned over by wind action, okay? So I don't know what the wind was on this particular day, but suppose we decreased the mixing due to wind and the waves and current and other processes. If we decrease the mixing, what would happen to these lines? Would they go deeper or shallower, these straight lines? If we decrease the mixing.
It would go shallower.
Go shallower. Likewise, if we increased mixing, they would go deeper, right? That makes sense. Okay, and so what this abrupt transition is telling us is that the water column is more or less evenly mixed from the surface down to some depth. And I'm going to say that this is like 50 meters, okay? Well, and then it starts to change, okay? And it's the temperature, the two properties are inclined. Incline is being the operative word. And so what we call this is we can describe this incline in or change of property as either a thermocline or a halocline. Halite, you know, being an abbreviation for salt. So there can be a thermocline or a halocline or a pycnocline, pycno being density. So this halocline is the point at which surface mixing is no longer uniform, and the stratification of the water due to its temperature and its salinity, you know, starts to take hold. So this thermocline area in this mixed zone turn out to be a really important component of ocean structure, seawater or water column structure. Is that clear? And so when we talk about a thermocline or a pycnocline or a halocline, we're describing variously the depth in the water at which, below which there's no longer even mixing, and the more static properties of temperature and salinity and the density stratification becomes more dominant. Okay? Well, why would S increase as we went deeper? Any ideas? So S is pretty small here, salinity, it's lower salinity at the surface than it is at depth, right? So the salinity has increased with depth. So what could be going on here? Any thoughts?
Colder water.
Colder water? Well, if it was colder, it would be denser, right? What could cause lower salinity in the ocean? How would you make, or if you had any water, how could you make it more or less saline?
Runoff of fresh water?
Runoff from fresh water or rain, okay? So if you were, and I don't remember where I took this CTD profile, but I'm guessing that it was fairly close to the Mississippi River. So the Mississippi is constantly putting fresh water into the ocean. Well, that fresh water is less dense than the seawater, so it tends to float on the surface. So you have less saline. So this is pretty typical a CTD profile. You have less saline water. It's being constantly mixed. The temperature is determined by some equilibrium with the atmosphere. And so these are constant over that range. And then when they start mixing, this fresh water is mixing with the whole volume of the deeper water. And so it rapidly decreases below the mixed zone. Same thing with the temperature. And so the salinity then is increasing as we go to greater depths. And the T, the temperature, is decreasing because this warmer water, or water that's warmed from the surface, is mixing with a much larger volume of colder water, okay? So that explains the S and the T, or the salinity and the temperature profiles in this overall CTD profile. Well, and here's something else. This is oxygen. And oxygen, of course, very important for all of us, very important for any heterotrophic organism, because oxygen is where we get our, what allows us to heterotrophically oxidize food particles. And you can see that in this profile, the oxygen is remaining constant over all the way from the top of the water all the way through this mixed zone. And then below the bottom of the mixed zone starts to increase. What do we think could be happening here? Where would this oxygen come from? Where does the oxygen come from? Any thoughts? So oxygen.
Autotrophs.
Huh?
Autotrophs like plankton and plants.
Some of them would come from that, but in this mixed zone, what does that imply? If you're mixed, you're at equilibrium with what?
The atmosphere?
The atmosphere, exactly. So the oxygen in the surface water is at equilibrium with the atmosphere. And, according to the solubility of oxygen in water, which is fairly high. Okay, so the oxygen in the surface, this surface zone of oxygen, is the same as, is at equilibrium with the atmosphere for the particular temperature and solubility of oxygen at that particular temperature and latitude. Okay? But then why would it increase? Somebody already said it. It increases because photosynthesis produces oxygen as a waste product. So what this is telling us is that there's high degree of photosynthesis right here, just under the mixed zone, right? And so there's actually a surplus of oxygen being created and released into the water column here underneath the mixed zone. So this is pretty typical also of a CTD profile, is sort of equilibrium concentrations with the atmosphere through the mixed zone, and then a little spike of increase underneath the mixed zone, which is where the plankton are hanging out, where they're effectively producing or photosynthesizing. And this water, this oxygen, extra water, is dissolving into the water, okay? And then it decreases and actually As you go further and further down in the water column, the oxygen will continue to decrease. Well, why would oxygen decrease in the water? It would decrease if the oxygen is being utilized. So what would the source be? It's being utilized to oxidize something. If it's being removed for the purposes of oxidation. Well, the main thing that's going to be removing oxygen from the water is going to be oxidation driven by what? Driven by organisms that utilize oxygen. And so what's happening, what you can see in this profile, and the way I'd like you to begin to learn to look at the ocean and think about the water column, is this sort of interaction with the surface, equilibrium, followed by processes that are occurring as we go deeper and deeper into the ocean. So actually, if we continue this down, continue drawing down, I think this stops at some arbitrary depth, like 200 meters. If we kept going down in the water, so let me imagine a water column, just like a little sketch up here. So this is the surface, and we were going down not 200 meters, but 2,000 meters. Okay, and let me point something out right here. So this is the way, very annoying that you do this. This is the surface, and this is the depth, right? So these numbers are actually negative numbers. And so, so this is the way that, we typically profile the water column. So 0 at the surface and deeper and deeper depths. Now these numbers technically are negative numbers, negative with respect to sea level, but their depth is typically not written with a negative number. But then when we draw this, we do it in such a way as to invert the x-axis, or show the y-axis rather, is going down on the page. All right, so let's go back to our drawing here. So a typical water column profile for oxygen would do something like this. Spike out, and then it would go down like that, and then like that. Okay, and so there's an oxygen minimum zone. It's usually about 1,000 meters deep. Okay. And that oxygen minimum zone is the region of the water column where the organic material produced by photosynthesis in the surface is being consumed and decomposed with the reduction in oxygen. And then as we get deeper into the water, the increase in pressure, the decrease in temperature means that the bottom of the ocean has higher levels of solubility. And so typically you see this oxygen curve that looks something like that. We'll talk more about that. But does that make sense to everybody? Everybody kind of got that big concept there. Oxygen coming from the atmosphere, and then a little peak of oxygen from localized photosynthesis. On the planet, on a sort of global scale, about half, about 45% of the oxygen produced on a daily basis comes from primary production in the ocean. And the other half, or actually about 55%, comes from primary production on land. So ocean primary production is pretty important for maintaining oxygen levels in the atmosphere, but it's not as important as primary production on land because the land area and the ocean area are so different in scale. Okay, so that's a water column profile. And then let's go back and think a little bit about what these numbers mean. So seawater is, the density of seawater, as we've said again and again and again now, depends on a combination of temperature, and salinity. So this allows us to do a little simple arithmetic. So pure water has a density of about 1,000 kilograms per cubic meter. It's the same density as 1 gram per cubic centimeter, just scaled up according to give it a, a bigger range and make some of the arithmetic that we're doing simpler. All right, well, we said that the seawater, the dissolved solids in seawater were present at a concentration of about 3.5%. So that means that seawater, if we assume an average salinity of 35 parts per thousand, then the density of seawater is going to increase. Seawater has a density that's increased by about 35 kilograms per cubic meter. Cold temperature can make the density as high as 1,070 kilograms per cubic meter. Okay? And so salinity and temperature, as we've seen in our little graph here, can occur in different combinations. So there can be different combinations of salinity and temperature within water depending on where it occurs and the forcing factors to which it's subjected. And so oceanographers are interested in the effect of salinity and temperature on density, sigma, in this equation here. So sigma ST is equal to the density, the actual measured density of seawater minus 1,000 kilograms per cubic meter. And we take away, we subtract this 1,000 kilograms per cubic meter, so that we're just looking at the changes of density due to the different effects of salinity and temperature. Okay? Why are we interested in this? Is it turns out that different water masses have different salinity and temperature signatures. Okay? Let's explore this a little bit more. So, and the other thing you can see here is that most of the change in density is due to the variation in temperature. Okay, so average seawater salinity, and let's see, can we see this here? Yeah, so average this is temperature. Yeah, so here's salinity on this graph. So the average salinity of the ocean can vary from 0 up to about 40. So in a Mediterranean ocean, a Mediterranean Sea where there's high rates of evaporation, the surface salinity can approach 40. Okay, let me just stop for a second and talk about the measurement of salinity and how we represent that. So I've been talking about salinity as using this number, the salinity number, 30, 40, 50, whatever. It's related to the concentration of solids in the water. And so, so this is salinity in not percent, but per mil. In actual use, we drop the units. And so we just talk about salinity as a practical seawater salinity unit. And so when we talk about salinity, we say 35, 40, and that is related to the concentration of dissolved solids. But for convenience and accuracy, we tend to drop that PPT. So when I say salinity, I'll talk about a salinity of 30 or 35. I say that the ocean has an average salinity of about 35. Well, that's parts per thousand or practical salinity units. Okay. All right. So this little bar here represents, this is the full possible range of ocean temperature. And then, you'll notice that for temperature, it's cut off here by the temperature of maximum density. You see, and at freshwater, the maximum density occurs at 4 degrees. As we introduce more and more salt to the water, the salinity increases, the temperature of maximum density decreases, and the temperature of maximum density actually decreases below 0, below, becomes a negative number here for very cold, very dense water. So at the bottom of the ocean near Antarctica, you would measure, not 0 degrees Celsius, but actually -2 Celsius. And that water doesn't freeze because of the presence of the salts. So this freezing point is raised. So now most of the ocean, in the Gulf of Mexico, the minimum temperature at the bottom of the ocean is about 4 degrees. In the abyssal plain, so out in the deep mid-Atlantic, the temperature would be the average temperature would be about 2 degrees, so somewhere along in here. So this bar here describes 90% of the ocean volumes. And so this is the range of salinity. So it's fairly narrow, from about 34 to about 35. And then this is the average salinity range, from about -2 to about -10. So this bar here, this this square, or this rectangle, it determines what the temperature is for the most of the water in the ocean. Okay. Well, the other thing to notice is if we're looking at density, so these contours here, getting back to our using and trying to understand what contours are. So these contours are sigma t, the change in density due to change in temperature. Mm-hmm. And so these are constants of temperature. Well, you can see that these are not straight lines. And they're not straight lines because density is actually being determined by multiple factors. Okay? And so we'll explore that in a little bit more. All right. Here's another way of looking at that. And this is something that pertains to the homework assignment that you have as a team. So here is temperature and here's salinity. And here we're looking at a salinity range of 35 to 33 to about 38, more or less, and a temperature range of 0 to 30. So this box is expanded beyond the range, the one that I showed you here. So the ocean surface has got a average temperature of somewhere between 25 and 30 degrees in this particular water column. So this solid line here, this heavy line here, is a profile of sigma t, and as we go, or sigma density rather, as we go deeper and deeper into the water. So here we are at 500 meters, here we are at 1,000 meters, here we are at 2,000 meters, here we are at 3,000 meters, etc. So this is the, this is the where that falls along these lines. And so then these curving lines here are the density that you would measure for the water at each of these depths. But what do we see? We see that these water is, that this is not a uniform, not a linear gradient at all, and that it's changing radically. The other thing that we see is that these lines of density are not straight lines, they're curved, as I pointed out in the previous slide. So if we think about the water and we think about the influence of the ocean, and different ocean properties and different regions of the ocean, we can understand intuitively anyway, and we can verify that with various examples. We can understand that water can come to have different temperatures and different salinities. Well, it turns out that temperature and salinity ocean tend to stay distinct, but these different combinations of temperature and salinity would produce different densities. Okay? So it would be possible to have two bodies of water that had the same density, but that density had been generated by different amounts or different arrangements, proportions of temperature and salinity. Is that clear? Anybody question that, not understand that? You repeat. So any particular body of water can have a density, will have a density determined by its salinity and temperature. But two bodies of water could have different temperatures and different densities, and different temperatures and different salinities, but the same density. Okay, so let's take an example. So let's say that we had one body of water here, we'll call this number 1, and this has a salinity of about just a little over 35, and a temperature of about, I don't know, 4, I guess. 4 is what this is. And so this has got a sigma, it's got a density of 1.028. And so if we follow this 1.028 line along here and consider a different body of water. So this is body of water number 2. This has the same density. Okay, it has the same density, but a temperature of about 12 degrees and a salinity of, you know, somewhere between 37 and 38 degrees. So, but the density is the same. Right? So here's the question. What happens if we mix this water with this water? Okay, now remember that this green line represents the, you know, is tracking the ocean characteristics as we go deeper and deeper in the water column. Okay? So remember, at the surface we have warm water. As we go deeper, the temperature decreases. Okay, and but the density, you know, so this is the, you know, this is the density. This line represents the density of the water as we get deeper and deeper in the water column. So the greatest density is near the bottom. But back to the question: what happens if we mix these two water bodies? What is the resulting water going to be? So we have two parent waters and we have a daughter water, a mixed water. Well, if we mix this water with this water, because these lines are convex, you know, with respect to our mixing, the mixed product is going to be denser than either of the parents. Anybody see that? Well, if the mixed water was denser than either of the two parent water bodies, what would happen to this mixture? Any ideas?
It'll be less dense.
Well, less dense would imply that it would be on this side of the line, right? But if you're mixing this with this.
I'm sorry, yeah, more dense.
More dense, okay. And if it's more dense, what's it gonna do?
Sink.
Sink, exactly. And so this process of mixing produces because of these convex lines of density, produces a product that's going to sink. And this process is called caballing, and the resulting water will sink. Okay, and so you'll have to solve the same problem in your homework, but I'd like you to do it and show that you can explain this same purpose. And here it is on a graph, so it shouldn't be too difficult. Okay, so this process of stratification by density, and you know this phenomenon that water bodies can mix together and produce a heavier off product is pretty key to understanding. We're going to go a little bit more into the different properties here in the next couple of slides. Any questions about what I've done so far? Okay, hearing no questions, we can start to build up a little vocabulary. Some of this I've already touched on. So the picnic line, water of different density forms separate layers. So the ocean, you know, this is a sort of assuming it's just a parcel of ocean, depth down to 4 kilometers, ocean bottom here. And so 80% of the ocean water is in this deep zone, 18% is in this picnic line, this changing density, and then about 2% of ocean water is in the surface zone. Okay? So picnic line is a thermocline, and picnic line is also a halocline. Okay? And remember, we showed in our CTD profile these same sorts of graphs at different scales. Okay? So those are some terms: picnic line, halocline, thermocline. And most commonly we talk about a thermocline because temperature is responsible for most of the change in water density, although salinity is very important, particularly for some processes. So why is the temperature almost uniform from the surface to about 200 meters? Well, because that's where this mixing zone, and this mixing zone, also called the epipelagic zone, is important. Now, other thing that happens is that typically, light energy is penetrating this water according to different properties of water, the way that water absorbs different amounts of different colors of light. And but as you get deeper and deeper in the ocean, the light is less able to penetrate the water. And so beyond a certain depth, there's not enough light present for photosynthesis to occur. So this epipelagic zone is very important for ocean productivity, primary productivity. And this mixed zone, the fact that the water is evenly mixed within this zone, is important for, supplying, trace elements, making trace elements available to photosynthesizing organisms. Trace elements like nutrients, like silicate, well, not silicate, but nitrate, phosphate. Okay. All right. So let's look at this a little bit. And this, again, will relate to your homework question. So, here are contours of the water in different arrangements. Okay, so here is a sort of a continuous, representation, a continuous profile of the water column that starts at some distance offshore. So here's, let's say that this is the land right here. The water goes up to the land, and this is starting at some point going offshore, measuring down to a certain depth. So in this region here, the bottom of this measurement is going to be the bottom of the ocean. So you can't make any measurements deeper than 80 meters here because that's the maximum depth of that particular portion. Okay, and so if we look at temperature, so here's temperature, and these are temperature contours, so constant temperature. So here's 14, here's 13, out here is 12. It's a little hard to see. Okay, and up here is like 15. There might be a 16 here. Okay, so that starts to make some sense. You have these contours. This is sort of a slice through the ocean, and at any one point, you've got a sort of a profile, a possibility of a profile. Now, in your homework assignment, what you're having to do is to look at a whole series of these profile measurements, and then to draw your own contours of temperature according to the measurements, so that you're going to have to interpolate or connect the dots in order to come up with the required lines of contour. And then the bottom is going to represent, where there's no more measurements, that's going to be a representation of the bottom. Okay, so here is a spring tide, and here is a neap tide. So spring tide is when the tides are particularly high and the water is moving particularly far inshore, and the neap tide is when it's offshore. Okay, so the seawater, the level of the ocean level, tidal level, is going to go up or down slightly in these two different, according to these two different tidal phases. But you can see that this has a big effect on the arrangement of these contours as we get closer or farther away from land. go backward a little bit. So here's the spring tide. The spring tide is bringing all this warm water, warm surface. So tides are mostly happening. Most of the effect of the tide is expressed in the surface waters. So when the tide is up, spring tide is up, you're going to see these contours of temperature closer to land. And then when it's down, these are going to be further away from land. All right? Same profile, same arrangement, two different tidal phases. We'll do a lot more on tides later on. Okay, so that's one way of thinking about it. So this is these are contours by depth, and so that the lines of the axes of this graph are depth and distance from land. Okay, well here's another compensation. Here's another way of looking at contours. So here's depth in meters. So this is not close to land. This is out in the open ocean. And this is comparing two decadal periods. So here's essentially the 1979 to 1999, so 120-year period, compared to 2000 versus 2015. So here's depth. And this is not distance from land, this is latitude. So we're going from 180, so here's the international date zone, decreasing west latitude, increasing east latitude. So this 180 or zero line tells us that we're right in the middle of the Pacific Ocean at a depth here, okay? And then on here is the temperature scale as a color. Okay, so here is the comparison of 1979 to 1999. Oop, I've lost my second graph here. What happened to my second period? Well, what happens is that this mass of warm water actually gets deeper. So that's an indication that the water has actually increased over time. And what this is showing us is that the maximum change is occurring at depths of around 150 meters. So the greatest degree of change comparing these two periods. I'm sorry, I've got my thing in front of me, so it's confusing me a little bit. Okay, so here's the white indicates no change. Positive numbers indicate a change in temperature. Negative numbers would indicate negative, blue colors would indicate changes in negative changes. So what this is saying is that in the Central Pacific, if we compare 1979, 1999 versus the same average over this more recent 15-year period, there's been an increase in water temperature. Okay, so these contours here are the delta, the difference in temperature comparing 1979 to 1999 with 2000, 2015. I think I kind of confused you a little bit with the way that I described that slide, but I hope I've straightened that out. Does everybody understand what I'm showing you here? So these contours are not contours of temperature, and they're not contours of depth. These are contours of change. Okay. Generally speaking, the ocean water has warmed, and that the largest expression of that open water can be warming water can be found already down at 150 meters. Some other ways of looking at ocean temperature. So here is the globe here. This is showing salinity and temperature. And you can see, just as you would expect, that temperature is greatest around the equator, whereas salinity, so look at how high the salinity is here. So this is the salinity. Remember I told you that the salinity in the Mediterranean and the Atlantic could be quite high, could approach almost 40 parts per thousand, 40 practical salinity units. Well, here that's being expressed. So typically speaking, the Central Atlantic and Gulf of Mexico is relatively saline compared to much of the rest of the ocean. So here's warm, salty water. And then here is relatively cold, fresher water. So the fresh water is coming down. And so we'll develop this in more detail. But fundamentally, what's happening in this part of the ocean is that this warm, salty water is mixing with this relatively cold, fresher water. Okay. So what happens if we mix relatively warm, salty water with relatively cold, fresher water when the two waters have constant density? What happens?
The water sinks.
Right. So what's going to happen is, like, you have a warm, salty water and a cold, fresher water. And they are, so these are two different bodies of water. And so these waters are mixing in the surface in this region here. This is the Labrador Sea, the Norwegian Sea, so there's the Labrador Sea. So this is where this mixing occurs. And we'll see that this is very important because deep water is being generated in this region. So you're mixing, you're having this caballing process occur at a great rate in these parts of in this part of the world. And it turns out that a great deal of what we call deep water is actually generated by this mixing process in this part of the world. So deep water generation occurs when this caballing process causes the resulting mixture of waters to sink. Okay, well, it looks like I've overshot my time again. A lot of material to cover, so we're going to have to wait until next week to talk about the different properties of oceans. And these things are in the notes. So are there any questions? Yes, Ronnie.
So on the homework, I'm a little confused by question number 3. There's a sigma. Are you asking what the depth distance change is going to be?
I don't remember what question number 3 is. Sorry.
It has to do with the chart, the salinity chart, temperature and salinity chart. Because you ask, like, what the temperature, the
this
salinity.
Is the team homework you're referring to, not the.
Yes.
Okay, hang on. Yeah, well, what's the approximate ST? Yeah, so this is the density. It's the density, the approximate density of due to salinity and temperature.
Okay. Thank you.
Because in this graph, we're concerned with the density as a result of both salinity and temperature. But when people talk about sigma T, they're talking about density due to temperature and assuming constant salinity. But for this example, because we're concerned with caballing, we have to consider both the contribution of salinity and the contribution of temperature to the water. Okay.
How is that different from question 2?
Huh?
How is that different from question 2?
What would the approximate density of the water? well, one is the density in grams per cubic meter, kilograms per cubic meter. And then, so, you know, what would the density be? And then sigma is, you know, is a derived number, right? Remember, you subtract 1,000 from the density, and that gives you the sigma.
Okay, got it now. Thank you.
Sure. Any other questions?
I had a question regarding the group homework.
Yeah, go ahead, Ryan.
Is that going to be due this week or is that next week?
That's going to be due this week. This is all about, you know, this is about water column structure and everything in here, you know, so I'm not talking about the carbonate system or anything like that. So this will be due this week.
Okay, I just didn't see anywhere to submit the group homework.
Carrie, can you?
I also just realized that, and I'm making a submission page now.
Ah, we caught you. Okay.
Okay, so that'll be due this Sunday then?
Yes, sir. So you guys need to get together and you know, work on this together. And then particularly this, you know, thing, I think will help, you know, if you work on this together.
Okay, thank you.
And keep in mind that this, this graph, you know, the one I showed you, the land was on the right, and on this, the land is on the left, okay? So distance from land, about 10 kilometers, 12, and so forth. So these are the distances in land, okay? And then the final measurement here is the indication of the bottom. So here, you know, the bottom is at about 31 meters, and here it's at about 33, and so forth. Okay. All right, everybody.
Quick question. When will we be able to get together to review our milestone 1 with you?
Carrie is going to make up a sign-up sheet, and the different teams can sign up. You know, I want to talk to the whole team at once. I think it'll work a lot better that way.
Yeah.
So Carrie will be, you know, will develop, and this is what we'll do. You know, there'll be several opportunities for, you know, consultation of the teams with either Carrie or myself. And that's a nice thing about this Zoom class. One nice thing about the Zoom class is that we can get together easily for these team conferences without requiring everybody to join up. Okay?
Right, thank you.
Great, thank you. All right.
I had one last quick question.
Yes, sir, Joshua, go ahead.
Could you go back to the temperature contours, the first set of temperature contours?
The first set of, oh, this?
Graphs. Your slides aren't changing.
Oh, okay. I'm sorry, I'm looking, I didn't share that screen, so. Just a second. All right, you see the slides now?
No.
I'm sorry.
And now there's no slides at all.
I know, this is operator error. We should get a new professor that's more adept with. Okay, now do you see them?
Yeah, yeah.
Okay, so which one do you want to go to?
Like the chart of temperature contours that was like a longer rectangle with the gray section. There you go. Yeah.
This one? Okay.
Contours in the water column.
All right, what's your question?
You cut out for a second when you said what the gray, like the gray section at the bottom of that graph represents. What is that? Exactly?
That's the bottom. It's the bottom of the ocean.
Okay. And how come that the darker blue or just like most of it just cuts off before it gets to the seafloor? People just.
So that means that's the maximum depth to which they lowered their CTD. So look, maybe they only had 100 meters of cable on their winch. So they couldn't get down any deeper than that. So that just means no measurement down here.
That's fair. All right, thank you. That's all.
Or either that or they cut that off just for clarity in this presentation.
Mm-hmm.
Make sense?
Yep. Thanks.
All right. Okay, everybody. See you. Have a good weekend. Carrie will put out the sign up announcement and a place to turn in the homeworks. See you later.
Bye.